Okay, so in this lesson, what I want to talk about are radioisotopes. So we've two parts to this word. So you have the radio part and then you have the isotope part. So I just want to focus on the isotope part first. So when we talk about iso means same, isotopes are, from an atom point of view, if we have a look here, so we have carbon. Okay, so we have what's called carbon 12, carbon 13, and carbon 14. Now, these are atoms of carbon, and what makes them atoms of carbon is the number of protons that are present within the nucleus of the atoms. So each of these have 6 protons, and because it has 6 protons, it's carbon. If it had more or less protons than 6, it would not be carbon, it would be a completely different element. But so essentially, if you like, the protons define the particular element. So in the case of carbon, carbon has 6 protons. Now, also as well within the nucleus, you have what are called the neutrons. And if we have a look here, so carbon 12 has 6, carbon 13 has 7, and carbon 14 has 8. So the number of neutrons can vary in atoms. And because the number of neutrons vary, that doesn't change it. It still is carbon because of the number of protons it has. But the number of neutrons can vary. And what happens is when we add these, so when you add the protons and the neutrons together, that gives you the mass number. So if we take, for example, carbon 12, the 12 comes from the number of neutrons, number of protons plus the number of neutrons. Carbon 13 comes from 13 is the mass number, and it's 6 protons and 7 neutrons. And then carbon 14 comes from it's 6 protons and 8 neutrons, which gives it carbon 14. So these are what are known as isotopes. Isotopes of carbon. So that's the first piece. So basically what distinguishes, you can have an element like carbon and it can have different isotopes. And the difference in the isotopes is determined by the number of neutrons that are present. They'll all have the same number of protons, in this case 6, but the number of neutrons will vary, and as a result of that, they will have slightly different masses. And it's this mass number that we normally stick on the end of isotopes. So for example, carbon 14, the 14 comes from the mass number. Carbon 13, the 13 is the mass number. And carbon 12, the mass number is 12. The only thing that's varying in each of these in relation to the nucleus of the atom is the number of neutrons that are present. And that's very key. Now, within the isotopes then, some of the isotopes are radioactive. So if you take some of the nuclei of isotopes are completely stable. They don't break down spontaneously and give off radiation. But some of them are not stable and they give off radiation. They emit particular types of radiation. Now, if we take in the case of carbon, so carbon 12 and carbon 13 are relatively stable, but carbon 14 is unstable. The nuclei in here is unstable. So this arrangement of protons and neutrons is unstable. So what will happen is this carbon 14 will just spontaneously start to give off, the nuclei will start to break down and it'll start to give off radiation so that it can turn into a more stable configuration. And when the isotopes are radioactive like that, when they're unstable, these are what are known as radioisotopes. And that's where this comes from. So the radio part relates to the fact that they're radioactive and they're unstable, and isotope comes from the fact that they're actually an isotope of a particular element. Now, if we think about it, so if we think about the atomic number, so the atomic number in the case of carbon is 6. So the atomic number is what distinguishes one element from another. Now, with isotopes, generally speaking, okay, when you have isotopes that have an atomic number of, let's say, 83 or greater, these groups are generally naturally they're naturally radioactive. So these are naturally radioactive. So when you have elements on the periodic table that are above, like that have an atomic number that's greater than 83, generally these are naturally radioactive, and they'll have isotopes that give off radiation. Now, when you have, so like let's say 84 and below, so isotopes that have a mass of less than 84, for example, like down the other side, um, that have an atomic number of less than 84, generally they will have at least one stable isotope. So generally speaking, as we go down the atomic numbers, the number of the isotopes of the particular element, there's more of them that become stable. Okay, but ones that are below 84 will generally have at least one stable isotope, and stable in meaning that the nuclei stays the same and it doesn't decay, or it doesn't undergo spontaneous breaking down and releasing of radiation like some of the other radioactive isotopes, such as carbon-14. So that's what we mean by that. So that's, if you like, that is what a radioisotope is. Now the next kind of idea that I want to introduce then is this idea of what is known as half-life. So half-life really relates to the lifespan of a sample of radioactive substance. So if we have a look here, so what we're looking at here is, imagine we have a sample of carbon-14, for example. So initially we will start off with 100%, let's say, carbon-14. So all of the atoms will be there and none of them will have undergo any kind of decay. Then after a period of time, which is known as the half-life, so a period of time which is known as the half-life, and that period of time can vary, what will happen is, if you're to look at your sample of carbon-14, half of the carbon-14 will have broken down or decayed, okay, and then 50% will have undergo spontaneous breaking down and releasing of radiation, and then 50% of it will remain. And then if we go another half-life and we look at the same sample, we'll have noticed of those, so this is the half that has not broken down yet, half of them will have broken down. Okay, so this half will have decayed, and then half of it will have remained. Okay, so if you see, so basically you start off with 100%, none of them broken down. After one half-life, 50% is broken down, and then 50% is remaining. Then after another half-life, of that half that's still remaining, half of it has broken down, and half of it is remaining, which is a quarter. And then if you take this quarter that's remaining and you look at it after another half-life, you will have like 12% of that will have remained. So this is like, so the blue part represents the amount of your sample, or the isotopes of carbon-14 that have not decayed yet, and then this whole portion that's in here is the amount of it that has decayed, and then the same thing after another half-life. So it's like, what happens is the amount of the amount of radioactive material that is actually present that hasn't undergone decay, it reduces by half each time. So the kind of like to look at this in a more concrete kind of way. So if we take, for example, here, so we can look at some of the half-life, so the time it actually takes for these substances to break down. So if you look at, for example, cobalt-60, so we can put this up here, so cobalt-60, and it has a half-life of, let's say, it's 5.26 years, so we'll just say its half-life is 5 years. Half-life is equal to 5 years. So what does that mean? Okay, so imagine we have a sample of cobalt 60, and cobalt 60, it's just made up of atoms um, of cobalt. So imagine these are our atoms. So we start off with 16. We start off with 16 cobalt atoms, and none of these atoms have decayed yet. And then imagine we fast forward. So this is our sample. We look at it, and this is what we start off with. This sample here. So none of them have decayed yet. And then we take this same sample and we look at it 5 years later. 5 years later, or after one half-life. And what we will actually notice is that, so imagine then, and I'll just highlight them. So after we've looked at it, we will find that 50% of them will have broken down, will have decayed. So I'll just, the ones that have decayed, I'll just put them in green here, like this. So we have, so what's going to happen is you're going to have, so these 8 here, so 8 of them will have broken down. So these will, over this period of time, they'll have broken down and released their radiation. So these will have broken down. And then these, so then you will have 8 that have not broken down. So that's these ones here. So essentially after one half-life, the amount of your cobalt 60 that has not broken down has reduced by 50%. And or another way to kind of think about it is that 50% of your cobalt 60 has undergone decay after one half-life, which is 5 years. So it takes 5 years for 50% of them to break down. So imagine we started off with 16, now we end up with just 8 that haven't broken down yet. 8 cobalt atoms that haven't broken down. And then imagine we go, let's say, so 2 half-lives. So we have 2 years. So this is after 10 years. So this is 10 years. So we go back and we look at this same sample. What we'll have noticed is that, so this number here, so this amount here that hasn't undergone decay, so these guys here, yeah. So half of them will actually have undergone decay as well. So you'll have all of these these have already undergone decay. But then, so 4 of these will have undergone decay as well. So these will all have broken down and split up. So these have all undergone nuclear decay and given off their radiation. So then after 10 years, you're only left with 4 atoms of cobalt 60 that have not undergone radioactive decay. And then that will continue on. If you go another half-life or another 5 years, so in 15 years, there'll only be 2 remaining. So that's what we mean. That's the concept of like looking at it at an example of half-life. And if we have a look here, so we can see, so these are just some other elements, some other isotopes or radioisotopes of other elements, and you can see that there's a wide variety of half-lives that are there. Okay, so some of them, for example, like if you take a sample for palladium, for example, 215, what will happen, like it only takes like 0.0018 of a second for half of the sample of the radioactive isotopes actually undergo to break down. If we look at sodium, it takes 15 hours. Iodine is 8.07 days. We looked at cobalt, it's 5.26 years. So it's quite long. If you look at radium, it's 1,600 years. So after 1,600, so imagine we replace this number here for 5 years with 1,600 years. And then uranium, for example, it's 4.5 billion years. So that that's a huge number. So if you think about it, for example, another way to think about it is that your sample remains radioactive, or it continues to give off radiation until for these long periods of time. So for example, uranium will continue to be radioactive for 4.5 billion years, and even longer it'll continue on being radioactive as well. So that's the idea. So that's the idea of what's known as the half-life of a radioactive isotope. So then really like just taking that into account, then here is your official definition of what we were talking about in relation to radioactivity. And this is something that you need to know as well, but you need to understand like what that actually means, the concept behind it. So the half-life of a radioactive isotope is the time taken for half of the atoms in the sample of the isotope to decay. So again, if we look at this example of cobalt-60, so cobalt-60 is a radioactive isotope, so that's a radioactive isotope. The time taken for half of the atoms, so the time taken, its half-life is, let's say, 5 years. So the time taken for half of the atoms in the sample in the isotope to decay. So if we start off with 16 atoms, it takes 5 years for half of those which is 8. So 8 atoms to undergo radioactive decay, or to decay. That's what they just used there. So then after another 5 years, for example, or after 2 half-lives, this will have split down in half, and half of those 8 will have undergone decay, and then you'll have ones that haven't undergone decay as well. And the thing is, as well, is so imagine this is our sample of cobalt-60. We don't know, like, there's no way of telling which one of these atoms of cobalt-60 is actually just going to undergo decay. It just happens spontaneously. So we can't predict, let's say, when an individual atom of cobalt-60, for example, will undergo decay, but we can understand, let's say, overall, or like when half of the atoms that are in the sample will undergo decay, the time it takes for that to happen. And again, like this here, if we have a look at this, so this is an example of, so we talked up here about carbon-14. So again, carbon-14 is a radioactive isotope of carbon, and we can see here, so this is just in a graph form. So we start off with 100, let's say, so we start off with our sample. We have 100% of the sample. So after 5,700 years, so 5,700 years is the half-life of carbon-14. So after 5,700 years, the amount of carbon-14 that we have left has reduced by 50%. Then if we go another 5,000 years, 5,700 years, the amount of carbon-14 that's remaining is 25%. And then if you go another 5,700 years, the remainder of carbon-14 is 12.5%. So basically, what happens to the other 50% of carbon-14? It has undergone radioactive decay, and it's changed into a different element, or the atom has changed into a different element, or it's undergone decay, depending on the type of decay that happens. So that is the idea of radioisotopes. So radioisotopes and the whole concept of half-life and what that means. And this here is your official definition that you need to know, and then this is just the explanation behind it. So that's what we mean. So hopefully that makes sense, and thank you for listening.